Hi everybody, my name is Greg Hancock, and along with my third eyeless friend, Patrick Curran, we make up Quantitude. We're a podcast dedicated to all things quantitative, ranging from the relevant to the completely irrelevant. In this first of 2 episodes, we lay the foundations of matrix algebra, mathematically and geometrically, and start connecting these important underlying ideas to statistics. Along the way, we also mention STDs, the 110 to the 10 to the 405, mystics, skin bags of water, Vector Victor, tack flashlights on a misty night, whoa, remembering mnemonics, Stephen Hawking, Bilbo Baggins, and my sultry voice. We hope you enjoy today's episode. All right, I know that we had Doug on a couple of episodes ago, but I'm still a little bit gun-shy about the whole audio thing.
I still don't know what happened. I sent him an email. We had it all set up. We had a backup recorder. We had the main recorder. And when I got all the audio afterwards, it sounded like he was in the bottom of a trash dumpster. So, yeah, I'm a little gun shy as well. We're just going to hope that the audio works on this one.
I will tell people out there that when we post-process and edit the episodes, there's often a lot of stuff that we go, oh, that's kind of cute. I wish we could keep that and all that. With Doug's, there was stuff that was like, I don't know what he said. Like he went on this whole thing about STDs, and I didn't know why he was talking about STDs. Turned out he was talking about SVDs, which stands for singular value decompositions. And he used the words a couple of times at some point to sort of make me understand them. But all of that stuff was just unintelligible and had to be cut.
So wait, you're telling me we weren't talking about STDs? Oh, that makes so much more sense now.
Oh,
never mind.
Awkward. Yeah. But it also got me thinking about the fact that in that episode, and in a number of other episodes, we make certain assumptions about people's familiarity with things. One of the things we make assumptions about is matrix algebra, and a lot of the language around matrix algebra, manipulations. And you and I do try to keep things at a conceptual level, but every once in a while we get into the weeds to varying degrees. So there's a part of me that thought it might be good to try to go together into the whole matrix algebra world. But then there's this other voice that says that's going to require even more mind's eye than usual.
Yeah, maybe we should start with something a little easier. You could describe some Monet prints so that people could envision them. Sure. Maybe some of your favorite Escher prints. I mean, let's start with something easier that requires visualization before going into matrix algebra. And you give me a hard time about requiring the mind's eye.
If I'm not mistaken, you had a mind's eye kind of story, a third eye kind of story that you have not shared. Is that correct?
You remember that.
Uh-huh.
Oh, man. So it was 100 years ago. I was in L.A. I was on postdoc at UCLA. So this would have been in 95, maybe.
Mm-hmm.
I was newly married. I mean, like 15 minutes newly married. We lived in Alhambra in the shadow of Dodger Stadium. And I had to drive to UCLA every day.
Mm-hmm.
That is the 110 to the 10 to the 405.
Sit down. Get back on San Vicente, take it to the 10, then switch over to the 405 and let it dump you out into Mulholland where you belong.
On a typical day, it's 90 minutes each way.
Wow.
It was 6 in the morning. There was a stoplight. There was a major intersection where cars were 3 lanes each way. I got the green light. I was first in line. I started to go forward, and something just didn't seem right. And I slammed on the brakes. And in a flash, a car went left to right in front of me through the red light.
Wow.
Probably going 60 miles an hour. It would have been a T-bone in the side.
Your side.
My side. And that would not have ended well. And so I kind of shook my head and went on. A few years later, my wife and I are pre-kid and we're at a bed and breakfast. Right, which is something that my wife loves and I less love. I love bed and breakfast if none of the people would be there, like including the hosts.
Yeah, right.
If you could just have the house. But we were sitting around in this mandatory kind of sitting in the living room where everyone is chatting. And there was a lovely couple who ran the B&B, but they were mystics. And they had dream catchers hanging and incense and all of this. And they started talking about third eyes. And my wife said, oh, well, my husband has a story about that. And so I briefly told it. And I said, yeah, it was just a sense I had to not go through. And the woman said, well, you saw it through your third eye. I said, no, I didn't. It just didn't feel right in the intersection. And she started to double down, and I started to double down on our perspectives. Mine turned into differential equations. The first and third lanes were slowing. The middle lane was speeding. There was a juxtaposition in velocity and acceleration, and I didn't like that. And she doubled down on my third eye, saw what was happening from above me. So I doubled down further, and I said, there's no such thing as a third eye. We are skin bags of water governed by random electrical impulses and molecules, and everyone is silent in the living room. And at one point, she just had this look of resignation, and she said, I never thought I would ever meet a person who was not born with a third eye. And then she walked out. So, yes, I have been told by a mystic that I was born without a third eye.
Wow.
Yeah.
Not just third eye blind. You don't even have a third eye.
And she said it with this sadness of just the weight of the world on her. I never thought I would meet someone born without a third eye. So are you going to ask me to use my third eye here?
Wow. Well, I do want to wade into, if I may, wade into the Matrix with you. It might require some third eye, but maybe it'll be my third eye.
Oh, I'm not... Dude. If we're going to do this, and you're going to force me to do this, okay. I know this is low-hanging fruit. This episode is The Matrix. Okay? So this writes itself. Red pill, blue pill.
Oh, and hang on a second. The phone's ringing. Hang on.
Dude, we're recording here.
I'm sorry, it's Michael.
Oh, crap.
Yeah, I know. Hang on.
This happened with Applebee's.
Yeah, hey, Michael, what's up? You're kidding. Really? Okay. No, maybe we'll try that. All right, thanks. Bye. Michael seems to think that there could be some legal concerns if we use the Matrix because...
Oh!
I know.
Seriously?
He had one suggestion, I don't know how you feel about it, that instead we refer to it as the Mättrix.
So it's like Simpsons when they did The Shining, yes. But to avoid getting sued, they had to do the shinin'.
You've got the shinin'.
You mean shining.
Shh. You want to get sued?
Oh, God. We were already a third-rate podcast, and so we're going to do the Mättrix?
That's what he said when we make explicit reference so as not to irritate Warner Brothers.
It sounds like an adjustable bed I'd buy my mom.
The Mättrix. All right. Well, let's give it a shot. Which pill do we take?
The red pill.
You take the blue pill. The story ends. You wake up in your bed and believe whatever you want to believe. You take the red pill. You stay in Wonderland. And I show you how deep the rabbit hole goes.
Let me ask you for starters, do you teach matrix algebra in your classes?
Oh, dude, I wrestle with this so hard.
Mm-hmm.
We talked about in Doug's episode, I told a little bit of the story. I used to have a hardcore multivariate stat where we did like 8 weeks of matrices.
Yeah.
I don't do that anymore, and it is missed. It's deeply missed because it's foundation to everything we do.
Yeah.
And so when I teach SEM and longitudinal SEM, I have a section on matrix algebra, but it's really basics. And that's it.
Mm-hmm.
And I'm actually struggling with that right now. How about you?
Yeah, I'm of such mixed minds on this for a variety of reasons. One is the students who take our courses, at least in my case, are a huge mix of people from all over campus and then a few people who are in our program. And so there's always that issue of where do you pitch the level of the course? And part of that has to do with the mathematics. So I wrestle with it. I consider it completely foundational, and yet I keep asking myself, how much depth do people who are applied researchers actually need? And I don't know what the right answer to that is. 2 ways that I have tried to resolve this are the following. One is for students in our own program, we have a separate course that includes all of the Matrix Foundation stuff paired with other content that is quite specific to people who are trying to become quantitative methodologists. So if I don't cover it in some of my classes, then I don't feel like I'm doing a huge disservice because I know some of those connections are going to be made in another class. But the other thing is, I want people to understand what the heck we're talking about. And so what I've tried to do, and I don't know how successful I am, but what I've tried to do is what I consider to be the equivalent of matrix algebra without the matrix algebra. And by that, I mean that all of the the matrix stuff, it's not going to come naturally. All of the matrix stuff that we do.
This is going to be a long hour if we keep doing this. How about as we'll do the matrix if it's a proper noun.
Okay.
And the matrix is even Warner Brothers can't sue us for saying psi is a K by K matrix.
All right. So if I say it with a lowercase m, it's matrix. If I say it with an uppercase m,
it's matrix.
Matrix. Okay. Good.
All right. Back on point.
Yeah. Sorry. So the matrix algebra that we're going to talk about is a representation of things that go on geometrically. And so what I try to do in my classes is rather than drag people through all of the matrix algebra, I try and help them to understand what's going on geometrically. And that is the equivalent of matrix algebra. It's just a way to try to visualize it. So that's my compromise, to provide the students in our own program the depth that they need mathematically elsewhere, and then to help people who I think are trying to be good researchers and make good, thoughtful choices to understand what's going on visually as much as possible. And I don't know that I'm doing it right.
I'm looking forward to hearing how you talk about that geometrically, because I don't do that. Mm-hmm. I'm particularly excited if you'll spend a couple of minutes on that, because I think there's a non-zero chance you'll stab yourself in the palm of the hand with a skewer again, since I saw that with an eigenvalue example you gave a while back. Setting that aside, I do see two motivations for understanding matrices from an applied user standpoint, right? If you're quanti, this is peeling back the layers of the onion and really seeing what's happened. If you're an applied user of these, for me, there are two advantages. One really is popping open the hood and understanding what's happening.
Yes.
There's a level of commitment of saying, okay, I'm going to take some control over this, right? This is what I'm doing. This is what I'm imposing on my data. And this is why this is happening. So one is a little bit more ethereal. The other is more practical, because you're going to get an error that says psi non-positive definite likely involves element 6-4. The hell does that mean? Exactly. You have an NPD psi. Well, what does that mean? Well, you need to understand the basics of matrices to understand, first psi represents this particular part of my model. Non-positive definite means this particular characteristic of the matrix. Now I have a really good sense of what the issue is and how I might go about fixing that.
So why don't we go through some basic terminology associated with matrix algebra, or linear algebra as it's sometimes called, and talk about the operations that we perform on those, and try to make anchors to things that are geometric, and try also to connect them to some of the statistical things that we do.
Good. Because like so many other things, we're going to take stuff that you all are completely familiar with, and we're going to rename it and use more occluded terminology, and then try to make you feel bad about not knowing it. So, business as usual, really.
Yeah, welcome. All right, so let's start off small. Scalar. Give me a definition of a scalar. What do you got?
A scalar, an individual number.
It is a number. Do you know why it's called a scalar?
I did not know this was going to be pop quiz.
Because when you multiply by that, it scales it, right? If it's a number greater than 1, it scales it up.
That.
If it's a number smaller than 1, it shrinks it. If it's negative, it actually scales it in the opposite direction. So yeah, it's called a scalar because it scales things.
Look at you, Mr. High School math teacher. I did not know that.
I'm trying to free your mind.
But this is the very first example, as all of you know what a number is, but we're going to bring it into the garage, sand it down, repaint it, bring it out, and call it a scalar.
There you go.
So a scalar is an individual number. What if I have more than one? How might I organize those in some systematic way?
Ooh. Well, one systematic way that you could organize them would be in a nice column that we would have, and that's sometimes referred to as a vector, like a data vector, right? If we have measurements for a bunch of people on a particular X variable and we put them all in a column like we typically do in our data file, then that would be a vector. It would be a vector that would have just one column, but as many rows as there are people. So there would be n. That would be an example of an n by 1 vector or column vector.
A Victor vector? Roger, Roger.
We have clearance, Clarence.
Roger, Roger. What's our vector, Victor?
Sorry, that one I'm legally bound to say. So you used n by 1, so we need a postal system, all right? Which means everybody needs an address, is where does each scalar reside? So that when we talk about an n by 1, there are n rows and 1 column. The first number we say are going to be the number of rows, and the second number we say are going to be the number of columns. So when Greg says an n by 1 vector, and if we assume n is sample size, which we often do in the kind of work that we do, an n by 1 vector means that there are n rows and a single column. All right, so it's always row by column. That's going to be our postal address system.
And we're going to use that very, very soon as things start to get a little bit messier. I would like to put a geometric spin on this.
This is your last chance. After this, there is no turning back.
Here we go. The word vector has meaning in other contexts. Maybe the word vector meant something to you outside of the math here. But a vector is sometimes used to represent an arrow, something that has a particular direction, something that has a particular magnitude. It exists in physics. It exists in a lot of different disciplines. So what I would like you to do is, and this is going to take some visualization, but I think you can do it.
I can only show you the door. You're the one that has to walk through it.
For all of our n people, however many people we have, n of them, I would like you to imagine each person has their own axis. So for simplicity, let's imagine there are 3 people. The first person I will call Al, and the second person I will call Beth, and the third person I will call Carl. So imagine that I have one axis that is Al's axis, and Al could have some score that falls along that axis. And Beth has some axis and has a score that can fall along that axis, and Carl has another axis. Now, these people are all independent of each other, so we're going to make their axes go out at right angles, just like you're used to doing when you think about things in 3 dimensions. Now, when I represent the data for Al, Beth, and Carl, what I'm going to do is figure out where along the first continuum is Al's score, and then Beth's score, and then Carl's score, and I'm going to draw an arrow that goes from the origin out to wherever that point is that is the corresponding location of Al's score, Beth's score, and Carl's score. So that is why it's called a vector, because those 3 numbers tell us where to go. If we're sitting at the origin, how are we going to drive out to where the data point is? And that's it. Now, if we had more people, n people, 100 people, 1,000 people, however many you have, it's harder to visualize, but we're doing the exact same thing. Every person has their own axis, and the data essentially give us a direction to point. If we're standing on the origin, we're going to go out to that place that is a location that has everybody's score represented by that ultimate point.
One of the most famous books ever written in factor analysis was by L.L. Thurstone, and the title is Vectors of Mind. It's one of my favorite titles of all time because it's the marrying of the statistics and the substantive work that we all do. So that is what he's referring to, are these vectors.
Exactly. So I would like to take an idea that you had and expand it out now. You had an idea of giving each element in that vector, that column vector, an address. So the second score down would be element 2, 1, because it's in the second row and the first column. But we only have one column in this example. What if we had many columns? What if we had p columns and it would be this array of numbers? Well, that's what we call a matrix. A matrix is like a bunch of column vectors all side by side. And the one that we're most familiar with is a data matrix.
We work with matrices all the time. If you have a calendar on your wall, the weeks are the rows and the days are the columns. And you go to the 3rd week and the 2nd day and it's Tuesday, you've done the 3-2 element of that matrix. So if somebody says, well, what is the 4-3 element of your data matrix? You go to the 4th row, you go to the 3rd column, and there's a little cubby hole that has the scalar that lives in that 4-3 element. The term I sometimes like of a matrix is it is a doubly ordered structure of scalars. And what that means is the doubly ordered is it's ordered by row and it's ordered by column. Now, as soon as we start thinking about that row by column, we can have rows and columns that are not equal to one another. That would be called a rectangular matrix. But we might have rows and columns that are equal to each other. And wait for it, it's a square matrix.
Ooh.
We work with square matrices every day. They're a correlation matrix. They're a covariance matrix.
Yeah.
It's P by P. So if N by P is your sample, N is the number of cases, P is the number of variables, P by P is a square matrix. So we can have a column vector, we can have a rectangular matrix, we can have a square matrix.
Couple of things I will add to that. First of all, the square matrices that you just talked about, they have a diagonal, right? The elements that go down 1, 1, 2, 2, 3, 3, all the way down. The thing that's nice about the matrices that you mentioned is that they're also symmetric. The elements above the diagonal, whether they're correlations or covariances, are the same as the elements below the diagonal, correlations or covariances. So for example, if we are in row 3, column 2, whatever that element is at that address, then that will be the same value as what would be in row 2, column 3. So everything above is symmetric relative to everything below.
Let's do a little notation because, of course, it's a podcast and we really want to start describing notation in addition to your vectors moving out into three-dimensional space. All right, we're all going to agree that if it's a lowercase letter that is neither italicized or bold, that's going to be a scalar. So lowercase x, just like if you type it into your computer, that equals 5. It's just a number. We're all going to agree that a lowercase letter that is bolded is going to represent a vector. And an uppercase letter that is bolded, then that means it's a full matrix with multiple rows and columns. So lowercase not bold is a number, lowercase bold is a vector, uppercase bold is a matrix. A lot of times, we don't want that column vector. We want to make it a row vector. So we're going to do a thing called a transpose. And it's super simple. Just walk up to it and shove it on its side. So where we had a little bold X, now we're going to put a prime sign next to it. X prime. When you see that, no matter where you are in the world, is if you see a bold X with a prime, that's now a row vector. It was an n by 1 vector. Now it is a 1 by n vector. But we can do that with a matrix as well. So if we have an n by p matrix X, X prime is a P by N matrix. All we do is we make the first column of the matrix the first row of the transposed matrix. The second column is the second row, and so on. And in a little bit, when we wander in this way, we're going to make huge use of transposes because that's going to allow us to do all sorts of really cool things when we start to manipulate our data.
So there are two roles that matrices play in our world. One is it's going to serve as an agent of transformation for other things. I'm going to hold off on that for just a minute. But I do want to think about it in the context of our data matrix. When we talked about a data vector, we had one column, right, where everybody had a score on X. Well, now we have an X1 and X2, X3, X4, X5, XP, right, as many as we have. I'm going to go back to that space that I defined where I did it for 3 dimensions for Al and Beth and Carl, but we could have it as many dimensions as there are cases, right? N dimensions. But I'm going to do the same thing for each of the columns. I am going to trace a vector from the origin out to wherever that point is that represents everybody's score on X1. And then I'm going to trace a vector out to the point that represents the score that everybody has on X2. And you know what? X2 might be in completely different units than X1. So it might go on for miles, whereas the one for X1 might be this stubby little thing. We'll talk about that in just a second. And I do it for X3 and X4 and X5. And I get this whole family of vectors, and they might be shooting off in very similar directions, or they might be shooting off in very, very different directions. And those directions that those are heading relative to each other are going to tell us something about the relation that those variables have with each other. Sometimes we talk about data rather than being in their natural metric as being in a standardized metric, right? Our old friend, the z-score. What the z-score does in this particular context is it gives all the variables the same units. So when I am plotting Al's z-score and Beth's z-score and Carl's z-score, I will have the same units for every person, every variable, And in the end, the vectors that I draw out won't be of different lengths. The vectors will all wind up being of the same length. So one of the benefits of standardization, just visually, is it makes all of the data vectors that are heading out, they're going to still be heading in the same direction as when the variables were in whatever their natural metric was, but it brings them in so that they're the same length. So standardization is a really helpful thing just in terms of imagining all of these vectors heading out the same distance.
Take those two variables and you do your clusters in the way you described and you draw those vectors, right? It's almost like it's a lightsaber if you ever go out in the backyard on a misty night and you have one of those tack flashlights and it looks like a... Okay, so maybe I've done that hypothetically. That's pretty cool. Think about two variables then that are uncorrelated, that they have no relation to one another. Well, those vectors are at 90 degrees. They go off forever, never to meet.
That's right, 90 degrees. They're perpendicular, or as we say, orthogonal.
As they get a little bit more related, well, they come a little closer to each other, and a little closer and a little closer. At the extreme, if those two variables are correlated 1.0, there's a single vector that's needed to run through those because one is a carbon copy of the other. It's really neat to think about the correlations in terms of the geometry of the angle between the two vectors that are associated with each of the observed measures.
And in fact, you could see it in your data matrix if you converted everything to z-scores, because if two things correlated 1.0, the columns of z-scores would be identical. They would map 1 to 1. So that's why when you draw that vector out there, when it's standardized, you're drawing the exact same vector, whether it's standardized x1 or standardized x2. And when they fall at right angles to each other, any two vectors that fall at right angles to each other are really just like the axis that defines Al and Beth and Carl. Those are at right angles to each other also because those people are independent. Well, when our data vectors are at right angles, it's the same idea that they are also assumed to be independent. Now, the cool thing that you should all go let your high school trigonometry teacher know is that you are using trigonometry right here. As Patrick said, the angle between two data vectors is extremely telling. Specifically, breathe through it.
This is my favorite thing. This is the only time in 30 years I use cosine.
No. Yes, exactly. It's the cosine. You told yourself you would never have any need for this in real life. This is it. Today's the day, cosine. The cosine of the angle between two vectors is, I don't mean it's like, it is the correlation between two variables. And when those variables are right smack on top of each other, have zero angle between them, the correlation is 1.0. And when the angle between two vectors is, let's say, 45 degrees, quick, punch it into your calculator. The cosine of 45 degrees, I think it's 0.707. And when they're at right angles, the cosine of 90 degrees is 0. And I'm getting so happy talking about angles between these things. What do you suppose happens if I have two vectors that are heading off in opposite directions? What would your gut tell you that is?
Negative?
Exactly right. And if they're headed in precisely opposite directions so that they actually fall in the same line, you would guess?
Negative 1.0?
Oh, look at you. Yes, exactly right. If there's a 180 degree angle between these two data vectors, then the cosine of 180 degrees is going to be a negative 1. And if you went to your standardized data just for simplicity and you looked at the columns of numbers there, on x1, when someone had a 2.5, on x2, they'd have a negative 2.5. If someone has a minus 1.2 on x1, then they have a positive 1.2. So everything there just flips. It is so beautiful.
This is the Matrix. Right? When he sees it?
He is the one.
When he sees all the things coming down, he's like, whoa, right? No, wait, maybe that was Bill and Ted's Excellent Adventure. I get those mixed up.
I like that you went with Matrix. You put an umlaut over it to give it more of a European flair.
What did we agreed on? I forgot.
The Matrix.
Let's go with Matrix.
Matrix. I like it.
All of these are puzzle pieces that click in together.
There are two other things I want to put in place, and then we can talk more about operations. One is that if you had a whole bunch of variables whose vectors were headed off in very similar directions, we know now that that means that they're very highly correlated. But start thinking about the analyses that we do, right? What does it mean when our x's are correlated or our predictors are correlated? That's going to be relevant for some of the statistical things that we're going to talk about in a little bit. The other thing that I will mention is that when you learned about cosine, you learned about it in the context of a right triangle. And you might have even had the, what is it called? What's the mnemonic? Yeah. You might have even had the mnemonic.
You need a way of remembering that.
That was good. So you might have even had the mnemonic device of SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So the cosine being the adjacent over the hypotenuse, what that really means in the context of two variable vectors is that the cosine of the angle is also the length of the projection that you would get if you projected one of those vectors onto the other, projected it on there so that it formed a right angle. So the length of that projection represents the correlation. If two vectors are at right angles, there is no projection of one vector on the other. And if they're right on top of each other, the projection is the full length of that vector, the full one unit of that. So just keeping that in mind too, that this correlation also represents the length of a projection.
Let's drag us kicking and screaming into, say, third grade math. We're going to start with our data matrix. Typically, we have X. All the model building that we do, all the model fitting, all the testing is all based on this N by P data matrix. But to do that, we need to start working in ways of combining certain things, maybe vectors, maybe matrices. So addition, subtraction, multiplication, and division.
The big four.
You're the high school math teacher. Why don't you walk us through that?
Well, back in my day, we didn't have all four of those, but I love it when people say, didn't you used to teach chemistry? I'm like, yeah, but there was only 18 elements. All right, so addition. Addition, whether we're talking about adding scalars or adding vectors or adding matrices, the main idea is that they have to be of the same dimensions, right? If you're adding scalars, well, that's what you were doing back in second grade, third grade. Adding vectors just means that you take all the corresponding elements and you add them together. So if you have one column vector and another column vector that is of the same length, the sum of those just means adding the corresponding elements and getting out a vector that is exactly the same size. So if you had a data vector x1 right next to it x2 and you wanted to create another thing that is the sum of those, great. That would be the sum of two vectors. And then for matrices, it's just the same idea that you've got a matrix. Let's say it's an n by p matrix. Doesn't have to be. It could be any dimensions. Adding that to another matrix requires that the other matrix be of the same dimensions, n by p. And then you just do it element by element. And that's it. That's matrix algebra addition done and done.
Another term just to confuse you is we often talk about the dimensions of the matrix, the rows and the columns. We talk about that as the order of the matrix. Well, the order is n by p, or it's p by p, or it's k by k, or whatever you might have. And to add two matrices, they have to be the same order. How I teach it is in your mind's eye, lay one matrix on top of the other and just add each of the elements that overlay. If they're not the same order, they don't cleanly lay on top of each other. So you can't add them. Mm-hmm. Subtraction, knock yourself out. A minus B, same thing. Just subtract B from A. Anything to add to that?
Not at all.
That's addition. That's subtraction. Multiplication. Now we start to mess with you, as multiplication of two matrices is actually very different.
Multiplication of matrices with other matrices or matrices with vectors starts to get a little bit into the weeds, and it doesn't follow rules that are intuitive. And I will say the words that go with it, but I'm not planning on doing much more than that. Instead, I'm going to transition into a geometric explanation. So let me start with the words that correspond to the operations. So let's say I have a vector, and I would like to multiply that by a matrix. And what I do is if I'm multiplying, let's say, matrix big A, capital A, I think Patrick said it has to be bold and capital, by a vector x, a lowercase x that's bold, In order to do that, I have to make sure that the number of columns in the matrix match the number of rows in the vector. So it is a one-to-one matching where you multiply each corresponding element going across the first row of the matrix by each element going down the column of your vector. And then you add all of those together. Whew, all right, there's a lot of stuff going on there. And that's an absolutely necessary thing to do for a lot of the manipulations that are going on under the hood in statistics. Geometrically, I would like to come back to just the idea of what a matrix is. And I talked about it as a collection of vectors, but it also serves a role when we multiply by a matrix. So imagine I have a vector in space. Could be a data vector, could be any other vector. When I multiply that vector by a matrix, what that matrix is actually doing is transforming that vector. It might be transforming that vector in terms of location, so it might rotate it to a different location. It might stretch that vector. It might shrink that vector. It might flip that vector. So the idea of multiplying a vector by a matrix is transforming it in some way.
The Transformers, more than meets the eye.
When I am talking about multiplying multiple matrices, we can think about it in a couple of ways. One is we can think about doing the transformation of one matrix on all of the vectors contained in the other. And that's not a bad way to think about it geometrically. The other, though, is that if one matrix represents a transformation when we apply it to some vector, and then we have another matrix that we also want to use, when you are multiplying two matrices together, all you are doing is compounding their transformations. So if one matrix rotated everything clockwise 90 degrees and another matrix rotated everything back 45 degrees, the matrix that you would get when you multiply those together just does the compound operation, which would be just rotating everything 45 degrees. So the idea of matrix multiplication is really just taking the transformation that each one represents, smushing it all together into what the final transformation would be.
The weird thing about multiplying is, as we just described with addition and subtraction, you take an m by p matrix, add it to an m by p matrix, and you get an n by p matrix, whatever those dimensions might be. Well, often you'll multiply two matrices of a particular order and get a matrix of a different order. And it goes toward what you're saying in transforming one as a function of the other. If our first matrix is n by p, our second multiplier has to start with p in its order. So the inside numbers on those orders have to be the same. So you could multiply an n by p by a p by k matrix. So those p's are the same on the inside. And what that means is the columns in the first matrix have to match the number of rows in the second matrix. But what's really cool is the outside numbers are going to give you the dimensions of your new matrix.
Right.
So if you have an n by p times a p by k, you're going to get an n by k matrix. We will commonly, and this happens, oh my gosh, all the time, x prime x. Well, what we're going to do is combine a transpose when we multiply it by itself. Well, x is n by p, so x prime is going to be p by n. And then we're going to multiply it by x, which is n by p, so the inside ends match, but our resulting matrix is going to be p by p.
Well, so let's transition. When we go from addition to subtraction, we go, it's just, sort of adding the opposite. When we go from multiplication to division, how do you explain that one?
This is a new ball game. Is addition and subtraction are easy. Multiplication, you're like, oh yeah, I see this. And division, we're kind of off to the races. The short description is there's not a direct corollary of dividing two matrices, so we're going to trick it by multiplying by the inverse of a matrix, which means we got to get an inverse of a matrix.
And the task is kind of a formidable one, and it requires a lot of math. Two things that I will say. One is that we're talking about inverses of square matrices here. The concept of an inverse of rectangular matrices exists. We're not talking about that. The thing that I will say geometrically about it, though, is like I mentioned before, a matrix can be thought of as this transformer, that when you multiply it by a vector or some other matrix, what it is doing is it is transforming it. It's rotating things. It's stretching things. The idea of an inverse of a matrix, so if A transforms something when you multiply it by A inverse undoes that. So whatever A did, A inverse takes it back to the original starting point. For that reason, when we have A times its own inverse using matrix multiplication, that nullifies whatever you did. It's as if you are multiplying by, I don't want to say nothing, but you're essentially leaving everything in identically the same place. And so when you multiply A times A inverse, or A inverse times A, you are left with a matrix that just has a bunch of ones down the diagonal, and it is called the identity matrix because it leaves anything you multiply by it in identically the same place as it started. But now if we talk about the matrix A divided by the matrix B, we don't literally do that. Instead, we do A times the inverse of B. And we're familiar with doing that in regular old math. If someone says, I want you to take 2 and divide it by 3, you know that that's like taking 2 and multiplying it by the inverse of 3. Well, it's the same idea here. A divided by B in terms of matrices is just A times the inverse of B, where the inverse of B is that matrix that undoes whatever B itself could do.
Imagine you're in middle school and you have 5x equals y, and you want to isolate x. Well, all of us look at it and say, oh, we divide 5, and so x equals y divided by 5. So you isolated x. Mm-hmm. Why we use these inverses often, not always, but often, is to solve unknowns in terms of knowns. So you have 5x equals y, we divide both sides. Well, the general rule is we can't literally divide two matrices. So that 5x equals y, we can multiply both sides by the inverse of 5, mm-hmm. which of course is 1/5. What is 5 times 5 inverse equals? Well, it equals 1.
Right.
And that's what Greg is saying is if you have A inverse, that equals the identity matrix. It's a square matrix. It has ones on the diagonal, zeros everywhere else. It's the matrix equivalent to the number 1. Mm-hmm. But on the right-hand side of the equal sign, now we have y times 5 inverse, which in our scalar algebra, we know is the same as y divided by 5. So that's all we're doing. It's a little bit of a Penn and Teller sleight of hands is saying, okay, if you're going to be a wiener and not let us divide by a matrix, well, screw you. I'm going to multiply by the inverse of a matrix, and let's see how you like me now.
How you like me now? How you like me now?
But those are the operations, right? We have addition, subtraction, multiplication, and division, and those get us pretty far. There are other things we do with matrices, though, also that are kind of specialized, and it seems worth mentioning them. They occur occasionally. Something called a trace, which just means you take a square matrix and you add up all the elements on the diagonal. That comes up in some of the derivations that we do. Something called a determinant is a little bit messier. How do you think of the determinant?
One thing that's confusing about the determinant of a matrix is no matter the dimensions of the matrix, so we're still talking square matrices, the determinant is a single numerical value. It's not a matrix, it's not a vector, it's a single numerical value that captures the general variance that is free in that matrix, independent variance in that matrix. The numerical value itself is almost always uninterpretable. It's not like I can compare my determinant to your determinant because this is scaled in whatever the scales of your measured variables are. So we often have a determinant of a covariance matrix or of a correlation matrix. And what we do know is the larger the value of the determinant, the greater the general variance, the independence is among the columns in that matrix. The smaller that determinant is, those vectors of yours that you so nicely described, they start collapsing on one another and they start getting closer and closer and closer. So when I teach it, I have a quick way of thinking about it. Imagine we had a 2x2 matrix. All right, so super simple. 2 variances and a covariance, all right? Now, again, I'm asking a lot here, but as you're driving, just picture in your mind's eye, not your third eye, because not all of us have third eyes. In your mind's eye, the first row we're going to denote A and B, and the second row we're going to denote C and D. A, B in the first row, C, D in the second row. So the diagonal is A and D. All right, those in a covariance matrix represent our variances, and then those off diagonal is going to represent a covariance. For that simple 2x2 matrix, the determinant is the product of the diagonal minus the product of the opposite diagonal. So A times D minus B times C is the determinant of that matrix. Now, as you go to 3x3, 4x4, hoo boy, it gets much more complicated.
Yeah.
Let's put some numbers in there. So the first row is going to be 2 and 3, and the second row is going to be 3 and 8. So the determinant is going to be 2 times 8. That's the diagonal. 2 times 8 is 16, minus 3 times 3, which is 9. All right, so we get a determinant there of 7. So there's some independence between the two. All right, let's go to the extreme. What if it is 2 and 0 and 0 and 8? All right, so 2 and 8 are the diagonal elements. 0 is the off diagonal. Those are Greg's 90-degree vectors.
Yep.
Well, 2 times 8 is 16. That's the diagonal, minus 0 times 0. Well, all of that variance is independent. 2 times 8 is 16. We're not subtracting anything. It's minus 0 because those are traveling off infinitely in 90-degree angles. So the third one, picture 2 and 4 and 4 and 8. So the first column is 2 and 4. The second column is just 2 times the first column, 4 and 8. Well, now the product of the diagonals, 2 times 8 is 16. We're going to subtract the product of the off diagonal, which is 4 times 4, 16. 16 minus 16 is 0. The determinant is 0. There is no general variance because one column is simply 2 times the other column. So I kind of like that way of thinking about a determinant is representing the generalized variance that exists in a P by P matrix.
And that already has some geometric spin to it, so yay you. I'm going to add a couple of more geometric pieces for those people who find it helpful. When you were describing your 3 examples, which I love, for the one where you had the orthogonal vectors, I think one was
2 and 0 and 0 and 8.
So that actually makes a rectangle that's 2 on one side and 8 on the other side. And the area of that rectangle is 16. That would be the determinant. When Patrick did some vectors that were not orthogonal to each other and computed the determinant, those could form a parallelogram rather than a rectangle. The area of that parallelogram is what the determinant is telling you. Now, as the vectors move closer and closer and closer to each other until they're on top of each other, what is the area of a parallelogram that's defined by 2 lines that are right on top of each other? The answer is there's no area. The determinant goes to 0. So the determinant can be thought of as the area of the rectangular parallelogram in the 2-dimensional space that Patrick described, or the volume of whatever the shape is when we move out to more dimensions. It becomes, instead of a parallelogram, it becomes what's called a parallelepiped. But then when I ask you what is the volume of something that is flat, there's no volume. So when one of the dimensions collapses in, boom, the determinant goes to 0. The other thing that I just want to reiterate that Patrick mentioned that is so hugely important is the idea of the determinant as representing that thing we call generalized variance. And forgetting about geometry in the way that I've been talking about in terms of vectors, just think of a scatter plot. And if we wanted to talk about just in general how poofy the data are in that scatter plot, the determinant of the correlation matrix, which would be in a standardized metric, gives us some sense of how big that cloud of points is. And as our scatter plot gets narrower and narrower and narrower, as our 2 variables get more and more correlated, things vary a whole lot less. The determinant gives us that sense. The determinant goes closer and closer to 0 as those variables relate more strongly. When we have a point cloud that is in 3 dimensions, or heck, just go all the way to p dimension, this p-dimensional point cloud, the determinant tells you how much variability there is overall. So it's a nice way to take the idea of variance and extend it to multiple dimensions.
This isn't like a pedagogical mechanism of going out 2 and up 8 and multiplying it to get 16. That's it. That is what we're doing. Now, let's then turn briefly to, so what? So what do we do with the determinant? It turns out to invert a matrix, you must have a non-zero determinant. You cannot invert a matrix if you have a 0 determinant.
Do not try and bend the spoon. That's impossible.
Not often do we get exactly zero determinants. We certainly can in our day-to-day life. What hassles us is when we have near zero determinants, and this often comes up in multicollinearity, variance inflation factors. Like, this stuff has its fingerprints everywhere. For those of you who use SEM programs, when you get that error message that says psi is not positive definite, cannot be inverted.
How about I give you the finger and you give me my phone call?
This is what's going on. If you have a determinant at or near zero and you cannot invert that matrix, the term you have is that matrix is non-positive definite, NPD. What that means is there's some linear dependency among the columns of that matrix, and you actually have problems. That's like a deal breaker. Again, that OLS regression coefficient vector is x prime x inverse x prime y. Well, we have that x prime x, which is now a p by p matrix that we have to invert. If there's a linear dependency among those columns, right? Let's say you have two predictors in your data matrix that are highly correlated. The determinant is near zero. You can't invert it, and you can't do your OLS regression.
Oh, yeah. Everything goes to hell, right? Because what your determinant is telling you is that even though you've got p dimensions worth of variables, you don't have p dimensions worth of behavior in those variables. They're starting to collapse on you, and it might be as simple as two things that are nearly perfectly correlated, but more likely it's some kind of multicollinearity that's really hard to observe just by inspecting things.
That's what's really hard is I will have a student come and say, I can't invert this matrix, but I look at the correlations and nothing is bigger than 0.58. And so I know it's not multicollinearity. And what I have to remind them of is the multi part.
Yeah.
Because Greg has been giving these wonderful descriptions of the vectors, but notice, listeners, he's never moved beyond 3 dimensions. Why? Because he and I are not Stephen Hawking.
If you are looking for trouble, you found it.
Yeah, just try me, you.
Oh! What about 4 dimensions or 5 dimensions or 6? That's the point of the multicollinearity. You don't have an Agatha Christie smoking gun. Oh, X1 and X3 are correlated 0.97. The drunken punch in the face is when you do this across the entire matrix, they combine in a way to say, dude, you have a P by P matrix. You do not deserve P by P independent dimensions. That there's an overlap in a way that is just going to jerk our chain.
I like that.
Okay, we got addition, we got subtraction, we have multiplication, we have division, we have inverses, and we have determinants. Do you know what that brings me to?
What?
We are at minute 85 in recording, and we haven't started talking yet about what the point of the episode is.
Oh, well, what do they do in the movies when that happens?
Oh, dude.
There you go.
The Matrix Part 2.
Part 2.
Part 2.
Of all the missions, you had to come walking into this one.
It's a sequel. I had to come.
Absolutely. I smell a sequel.
Oh, we're going to milk this for all it's worth. If we didn't hemorrhage money on this out of our own personal bank accounts, this would be like a payday.
That's right.
It's going to be part 2. Did I ever tell you I went to the movie with my wife of the first of the Hobbit?
Oh, yeah.
Right? So this was years ago. There's all the action and everything, and then like the little Hobbit friends are all together. And they walk off in the field, and it's like, oh, Bilbo, you're my friend. And oh, whatever, you're my friend too. And they walk into the field, and they start running the credits. And I was like, son of a bitch, what happens? I had no idea it was a freaking trilogy. I had to sit through like 6 more hours to figure out if he was going to throw the ring into the volcano. So, yes, this is like little Bilbo Baggins is going to walk off into the field.
Sam, I'm glad you're with me.
When looking for that clip in post-processing, I realized I confused the movies The Hobbit with Lord of the Rings and Bilbo Baggins with Frodo Baggins. On behalf of Quantitude, I apologize. Please direct all complaints to grhancock@quantitudepod.org. And we're going to come back next week, and we're going to say, okay, we've got this whole architecture now that we built. What are we going to do with it? How do we use this to our advantage? The sequel.
Ooh.
I told you to stop doing that. That weirds me out.
You still don't like my sexy sultry voice. Next week on Quantitude.
Thanks, everybody. We're gonna call it here.
The Matrix
right.
Part 2.
Shut things down. We hope this has been of some use. I know it's like weirdo town to do matrix algebra while you're driving from the 110 to the 10 to the 405.
At this time of day, it's gonna be jammed. Are you crazy?
As always, thanks for your time, and we will start this conversation next week.
Thanks, everybody. Take care.
Oh, God. Help me. Help.
Nope. We can't do that. Can't do that.
Thank you so much for listening. You can subscribe to Quantitude on Apple Podcasts, Spotify, or wherever you download playlists for your upcoming spring break road trip, and please leave us a review. You can also follow us on Twitter. We are at QuantitudePod. And visit us on the intertube at quantitudepod.org for past episodes, searchable playlists, show notes, and newly available transcripts, and other cool stuff. Finally, you can get ridiculously fun Quantitude merch at redbubble.com, where all proceeds go to donors choose to support low-income schools. You have been listening to Quantitude. Even if you intentionally try to mispronounce us, we still come out as Quantitude. Quantitude has been brought to you by Quantitude Brothers Studios. Created after the surprising success of The Matrix, QBS is proud to bring you upcoming releases including Sheepless in Seattle, Citizen Kanye, Starwarts, Apocalypse Panel, The Godfeather, and Shaving Ryan's Privates. By Third Eye Prosthetics. Do you have a loved one who suffers from the complete and total inability to introspect or take viewpoints beyond whatever is sitting directly in front of them? Founded out of sheer frustration by Greg and Patrick's wives, Third Eye Prosthetics can help. And by Eigenvalues and Eigenvectors, who would like to let you know that in next week's episode, they are going to you up. This is most definitely not NPR.